You're given a string of some valid expressions. These expressions, for the purpose of discussion, could be either a bracket, could be either a pair of curly braces or a pair of parentheses. So using the terminologies given in the textbook, these are what we call expressions. You're writing a methods or functions to see if a string of these expressions are balanced. So what does that mean? First of all, a balanced expression means that you have a valid pair of them, a valid pair of parentheses like this, right? Or a valid pair of curly braces or a valid pair of brackets. So these are balanced. This is what we mean by balance. Let's say if you have a Java string str, and this str has these things in it. Open, right? This is what we call open, and then open curly, and then close curly, and then close, right? So this is open. This is what we call close. So whatever they are, this is open parentheses and then close parentheses. So you're writing a function basically to check to see if these simple pairings exist in the string. Just to simplify the problem, we don't have any English alphabet in there, like A, B, or 1, 2, or 3, alphanumeric, none of that stuff, just these symbols. You're checking if the conditions are true, whether they are correctly ordered, meaning there is open one and closed one. You cannot have a string that has an open, basically a string that has a close bracket to start with, right? So the order is incorrect. So this is not good. This balance function is going to return false. This is condition number one. Condition number two is checking to see if they have the correct pairing. So every open brace has a closing one, meaning if there's an open one, at some point there's a closing one. If this is the case, then it's true, right? The third condition is checking to see if these symbols have parentheses does not close with a closing curly braces. If you have an open bracket, you can't have a closed non-bracket. So this is false. So we want to write a function. We can use what's called a stack to keep track of them. It's worth illustrating this and just get this in your thought prior to implementing anything. Just to simplify this, let's say we have a string, and this string is like so. There's some stuff in it. This is str. On the other side, we have the stack. This is our approach or the algorithm. When we see an opening expression, as soon as we read it, so this is your read pointer, right? It starts reading from left to right. You immediately pop that opening expression into a stack. Let's say, at step number 2, your read pointer now is at what? At the very next one. This is the read pointer. Well, first of all, you have curly. Now you have bracket. So what will happen is your stack at this point would have both the curly and the bracket in it. This is what I want you to maintain. The reason why this is useful is because stack actually maintains all of the history of your logic. Moving forward, there's step number 3 somewhere, but step number 4. Step number 4 means that your pointer is now at the 4th location. Let's say if you have the 4th one is the parentheses. Actually, the 3rd one is the parentheses, and the 4th one is a closing one. So what will happen is as soon as you land on something that is closed, this is close, right? You pop whatever is in the stack. So what will happen at this point is you have curly first, you have bracket, and the 3rd one is open parentheses. So without adding any more to it, this means that you would push something to that stack. Instead of pushing this close parentheses, which is a close expression, in other words, you will want to pop it. You will want to pop whatever is in the stack. So this is the algorithm. So as you can see, every time you encounter a closed expression, you pop it off of the stack. This will give you all of the remaining open expressions. And if at the end of your read, at some point, you are done with your reading and your stack is also empty, that means you have effectively come across a complete paired or balanced expressions. Therefore, your function will return true. At the end of your read, if you still have anything left in the stack, that means you've got unbalanced bracket expressions that exist in the string inputs, then your function will return false. Okay, so I hope this illustrates it. Let me close this one. You can review your video later on. So this is my Visual Studio Code. It has basically nothing other than just a main. So what we want to do is build a public static. Since this is all static, it'd be a lot easier to write it that way. And just say that this function is called its balance. This balance is taking in an input string, and this returns some Boolean. I'm just going to return false right now, see if we can compile at least. And what we want to do is just system output line this, right? Its balance returns a Boolean. I can just artificially hard code this. Let's say, I want this as my input argument. My Boolean should come out false. It is false because we haven't added anything yet. So this is pretty generic and pretty dumb at this point. So let's make it smarter. Notice that if your input string is a even number, then this is not in pair. You should return a false. If your string is a null, meaning there's nothing in it, it's not a balance, right? In that case, you can return false. First thing to do is check and see if this is null, or if the string itself having odd number, right? So how do you check for odd number? You multiply by 2, see the remainder is 0 now, right? This is not, then return false. This is the very first thing you can do. So in other words, you can double check and it does return a false. The function actually exit right here. So this is actually correct logic in here. What if you have even number of string and this string also is not null? Okay, so let's just use stack. Stack is available in your Java util stack. There's a lot of ways you can implement this. Is you can use what's called DAC and then linked list. For simplicity, let's just use stack. A string is a collection or array of characters. By the way, generic requires a class. So you have to say character and not char. Using char is going to be wrong. And then we're going to call this in the stack. This is how you use the Java templates using generic to instantiate this. You can leave this character in there. If you want to be super careful, you can always add characters in it. So this is how you pass generics in it. And this is our character stack. So what we want to do is be able to loop through our entire string. How do you do that? We want to convert our string into a character buffer and then iterate through that entire buffer one at a time. You can actually write this. So instead of writing a for loop with an index, you have to convert this to a char array. This gives you the ability to kind of iterate through every single characters in there, just to make sure that we have this in the right spot, right? Let's just print it for the hell of it. Okay. Oh, actually, this one is not done yet. This entire thing exit right here. That's why you don't see it. But let's just make sure that we have at least some stuff in it that are in the even numbers. This means that this actually works. If this C is a open, right? Open is this. We have 3 types: braces, brackets, and parentheses. These are open. So if we come across any of these open ones, what do? We push them into the stack. So this is according to our algorithms, right? This is equals curly right here. Or if C equals curly braces, in no particular order, doesn't matter. C equals bracket. We stack push. Now stack is a collection of characters. It uses characters, so we can push this in readily. That's the if. But what about else? If the character is not, like we said before, right? It's not the open one. It's got to be a closed one. So we got to check to see if the stack is empty at this point. There's nothing further to check. You can pretty much return it at that point. If stack is empty, let's just say this. This is much easier to understand. If you still have characters left, but stack is already empty, it's actually false at this point, because that says, hey, something is wrong. There's got to be some unbalanced expressions elsewhere. So we can pretty much exit there. But what if stack is not empty and for some reason, when you peek this, stack peek means just taking a look at it. When you peek into it, you're getting this. Your C at this point is actually the closing one. You have a open curly and a closed curly from reading. So this tells you that this is a valid conditions for what? For stack pop, right? So this is according to our algorithm that we discussed earlier. But this only works for curlies? No, right? Because we have bracket and parentheses as well. So we want to expand this by adding more use cases here. So let's just make sure that we get this. This is not in, this is or, right? So let me just cut and paste this because I know this is pretty hard to type sometimes when you have a lot of curly braces here. So the second situation is where you have open bracket in your stack and you have a closed one when you read them. The third one is for the same logic, but with respect to parentheses. You can say, hey, I want a stack pop. So hopefully everyone can see the logic. Sometimes when you kind of break them up, it becomes hard to read. Let's check to see if the logic is correct. Pretty sure this is all correct, because when you look at this, if the read produces an open expression, when we inline this, we didn't make it pretty. If you're on a Mac, you can use Option Shift and F to beautify this. The stack push is fine, but if this C read, your reading pointer, is not a open expression, then you want to check to see if stack is actually empty or not. If not empty, then you check to see if now you have a pair that you're looking at. If so, then you stack pop it. Assuming you're done through the entire loop, you're left with a stack. This stack could be either empty or not. So if the stack at this point at line 26 is already empty, then you're cool, right? But if the stack is still got stuff in it, that means your original buffer is not a balanced expression. In that case, to express the dual logic, you can simply return whether stack is empty or not, right? If this is empty, then yes, it's true at this point. You have to account for various different logics where the solutions may be. Checking for this, we see that the output is true because this is all balanced. But if you just make it unbalanced, let's say 1, this should be false, right? But let's say if you have another one that is even number but is not balanced, in this case, you don't have a close one that matches it, you get a false one. So let's just do a couple more. So if we go back to parentheses, right? So let's just make it a couple of those. I won't be going into other cases, but you guys can run more of those on your own. So this completes the code demo for the balanced expressions.